There's a TV show started maybe 40, 50 years ago. I don't know. It's been around for a while. It started out as a comedy show, and then it maybe wasn't quite so much comedy anymore, but I think it's back to comedy again. Sound familiar? It's on Saturday night. Yes, it's Saturday Night Live. They had some really great comedians there initially. John Belushi, of course, comes up. Chevy Chase, Dan Aykroyd, one of my favorites. Jane Curtin, Gilda Radner. There was quite a collection of them. They all went on to do big things. But there was one comic that didn't really get as much airplay. He wasn't a regular, but he came on once in a while. He was called Guido Sarducci. Now, he sounded like he was from Italy, from the Vatican, actually. But you could tell from his accent that he was really like from the Bronx or something. But he came out and he would do this shtick. He had this papal vestment and he had this great big hat that come out like this, all like this, and had a big beard and a flowing mustache. He smoked a cigarette all the time. He had this shtick. He had this thing where he talked about the 5-minute university. And into the 5-minute university, you learn everything that you're going to remember 5 years out of college. Think about that. In a 5 minutes, that's all you're going to remember in a 5 years. Into this university, he had a bunch of different classes. He had a class in economics. In economics, you learn a supply and a demand. And really, that's all you need to know about economics. You learn that when the supply goes down, the price goes up. When the demand goes down, the price goes down. We saw that with the gasolina that we had a little while ago. Well, he also had a course in business. In a business, you learn a buy low, a sell high. Buy low, sell. I have a trouble with this one. I've never been such a good businessman. What else? He had a class in Spanish. And you learn ¿Cómo está usted? And the answer, she's muy bien. Y tú? Try that with me now. ¿Cómo está usted? Muy bueno. He had another class. Excuse me. He had another class. Well, actually, he didn't have another class. He should have had a class in a color theory. And if he did have a class in a color theory, it would have been this. Light, she comes in 3 flavors. There's a red, there's a green, and there's a blue. And that's all you need to know about a color. Everything that you see, every color that you see is made up of some combination of red and a green and a blue. That's where we're going to start today. We're going to learn the RGB color theory.
Warning. Virtually everything in this presentation is a lie.
But it's a good lie. Here's a statement of RGB color theory. The RGB color lie. Light is 3 flavors. Red, green, or blue. That's all there are. And everything that we see, all colors that we can imagine, are combinations of some amount of these 3 flavors. Let's demonstrate that. I'm going to turn my camera around to try to see my display. There we see my big display. And I'm going to bring in a second camera here. This is a little USB camera. It's an optical microscope. And I'll bring that one up on the screen here so we can see both of them together. And let's have a look at what this white patch looks like. A little hard to focus, but there you can see red, green, and blue pixels. That white on the computer monitor is made by mixing equal amounts of red, green, and blue. And if I take a look at this red is made up of red pixels. Go figure. Green, oh, that's made up of green pixels. Does somebody want to take a guess as to what the blue one might be made of? Let's see. We make blue by turning on all of the blue pixels on the computer monitor. That's all we have. Red, green, and blue pixels. How about some other colors? Let's look at black. What do we do? Okay, so we turn on no pixels in order to get black. That kind of makes sense. Let's look at cyan now. Somebody want to take a guess? What do you think? How do we make cyan on a computer monitor? I heard somebody say green and blue, and that would be the correct answer. Green and blue make cyan. Okay, magenta next. What do you think? Kind of looks like purple, red, and blue maybe might be a good mix. Let's see what we get, how we get magenta. Yep, red and blue, it is, yes. Okay, now, yellow is a little bit covered up. Hang on just a moment. Okay, let's see how we make, does somebody want to take a guess? Think about that for a while. How is it that we would get yellow? Have you guessed yet? We'll come in now. Here we go. Here we go. Oh. Yellow is made by mixing red and green. That kind of makes sense because that's what's left. But it doesn't feel right, you know? I've looked at tablet screens, and I've looked at cell phones, and I've looked at televisions, and I've looked at all kinds of different computer monitors, and they all look the same, more or less. When you get up really close, you see that light that comes out of any of these screens is made up of some combination of red and green and blue. This might be fun. Let's take a look at the rainbow. I'm going to start over here on this side. Here we have red. All we see there is the red pixels. And as I move a little bit over, now I'm starting to see a little bit of green, a little bit more green. Now the green is pretty prominent. I'm here in the orange, and I've got a fair amount of both. Yellow, I'm seeing about an equal amount of red and green. Now the red is backing off a little bit as we get closer and closer to green. Now the now the red is very dim, pure green. Move over here, we're starting to get a little bit of blue. You can just barely see the blue now. When I get into the cyan part of the rainbow, now we have a fair amount of blue. There we see perhaps an equal amount of the two. And as I move further, now I just have blue. And as I come here, there's a little bit of red, a little bit more red. And there, purple's made with a combination of the blue and the red. This demonstrates that with computer monitors, televisions, tablets, cell phones, all of these devices, all they use are red, green, and blue pixels. All of the colors that are available on a TV, when you're watching YouTube, all of these colors are available by just mixing the three flavors of light in some proportion. This proves the premise about RGB being the three flavors of light. We see the same thing on computer interfaces. The basic interface that we see in Windows, I'm running PowerPoint right now, that basic interface has a combination of red, green, and blue. And every color, in this case cyan, is made up of some combination of those. Here we have very little, actually no red, and full-on 255 of green and blue. I could adjust this to get any color that I want, any of the colors that are available on my screen. Let's review the rules that we came up with for mixing colors. White was made up of a combination of red, green, and blue, full on of all of those. Red, of course we make that with just red pixels. Green, green pixels, blue with blue pixels. Cyan we saw to be a mixture of green and blue. Black was none, and some of the more complicated ones, let's go on. Magenta is made up of red and blue pixels. And then finally we have yellow. This one's a little bit confusing. And we'll get back to that. I think by the end of this lecture, you'll understand why that is. But I remember back in kindergarten, mixing paints, mixing finger paints. It was a lot of fun, but most of the mixtures we got were mud. And I seem to remember that red and green is kind of a brownish color, not a very particularly pretty color. How does that explain it? That doesn't jibe with what I know about yellow. So we'll get back to that. This diagram is a prettier, maybe more memorable version of that table. We have red, green, and blue. When we mix red and green, we get yellow. When we mix red and blue, we get magenta. And when we mix blue and green, we get cyan. All three of them together, we get white, and none of them, we get black. Let's try this with flashlights. All you need to try this at home is 3 flashlights. 3 of those little tactical flashlights. This one I took apart and I put a little blue filter in it. The next one I took apart, I put a green filter in it. And the third one, I put a red filter in it. Now if I turn them on, we see that a mixture of green and red gives us yellow. If I mix, let's see, this combination, red and blue, I get magenta. And finally, if I mix green and blue, I get cyan. And if I can figure out how to mix all 3 of them together, I can get something that looks like white, kind of. I think this pretty well establishes our premise that light is made up of 3 flavors, and every color that we see is some combination of red, green, and blue. Are you ready to be confused? Let's play with filters. I'm going to start off with a Kindle, and I'm going to use that Kindle as a light box. On that light box, I'm going to put 3 filters, and as you might guess, one of them is going to be a red filter, another one is going to be a green filter, and finally, we're going to have a blue filter. We're going to play with combining these filters. Let's just say that I were to take the, let's go with the red and the blue filter, and I'm going to put one of these on top of the other. Now, what do we expect? We saw before that when we mixed red and blue, that one was magenta. So if I turn on red pixels and blue pixels on a computer monitor, I get magenta. So let's see what we get here. That does not look like magenta. To me, that looks like black. Let's try another combination. Maybe this just doesn't work out for those 2. Let's try the blue one and the green one. And let's see, with blue and green, we got, help me out, guys, here. We got cyan, right? Okay, so let's put the blue on top of the green. And we did not get cyan, we got black. All right, last shot here. The last combination is the red and the green, which surprisingly gave us yellow. We mix red and green pixels on a screen, and we get yellow. But when we mix the filters, we get a delicious shade of black. And if I put all of these together, we see that all roads lead to black. This doesn't make sense at all. How do we explain that? Let's just talk about filters for a little while. Does anybody out there have any filters? No. Does anybody drink coffee? Oh yeah, coffee filters. Coffee filters will pass coffee and keep the grounds from going through. So the grounds don't pass and the coffee passes. Anybody else have a filter? Somebody own a car? Yeah, in a car we have an oil filter, and that passes oil and it captures all of the sludge, the dirt and all that kind of stuff. In my furnace, I have a filter. It's an air filter. It captures the dust that's in the air and it passes the air. So let's see, coffee filter passes coffee, an oil filter passes oil, and an air filter passes air. What do we think a red filter does? Let's apply our red, green, blue color theory to this. Here we have a red filter, and on this side we have white light coming up to it, a combination of red, green, and blue light, and it passes the red light. The green and the blue light don't pass through. Simple enough. Green filter, basically the same thing. We got white light coming up to it, red, green, and blue, and only the green light goes through. Finally, we have a blue filter. White light, red, green, and blue, and only the blue comes through. What happens when I combine a red and a blue filter? Well, let's see. The red filter here, we're seeing red, green, and blue light come up to it. It will only pass the red light onto the blue filter. Now, the blue filter is only going to pass blue light, and the blue light did not pass through, so there's nothing left to pass through the blue filter. Red and blue, when we mix them as filters, we get black. The thing is, when we're adding filters, we're not really adding them, not in the same sense that we add light when we turn on pixels on a TV. So different rules apply. Filters block light rather than add light. They subtract. So if you combine red, green, and blue in any combination, you get just black, nothing else. How about a cyan filter? I just happen to have a cyan filter here, and a yellow one, and a magenta one. And I apologized for the camera here, because this yellow isn't quite the yellow that I would like it to be on the camera. The cyan is a little too weak, and the magenta looks more like purple. Like I said, I apologize for the camera, and it is the camera's fault. That's something that we're going to talk about later in the semester, about how cameras are not as color faithful as we would like to be. But let's talk about that cyan filter. If a coffee filter passes coffee, and an oil filter passes oil, and a red filter passes red, then a cyan filter should pass cyan. But we know from the RGB color theory, which I remind you is a lie, that there ain't no such thing as cyan light. Let's go back to our table here. Cyan, whenever we see that, we know that it's a combination of green and blue light. So that means that a cyan filter will block the red light. Red light is not going to go through a cyan filter, but green and blue light will go through, and we see on the other side a combination of green and blue. The same sort of thing applies with a magenta filter. Light that's red, green, and blue, in other words, white light, hits the magenta filter. The red and the blue come through because red plus blue equals magenta, and the green gets blocked. Finally, with a yellow filter, same thing. Red, green, and blue light come up to the yellow filter, and the blue light gets blocked. Red and green pass through because red and green make yellow. Let's put on those old thinking caps and think about what happens when we mix, when we combine when we put a magenta filter on top of a yellow filter, what do we expect to happen? Well, let's see. That magenta filter is going to pass the red and the blue, but not the green. So red and blue light proceed to the yellow filter. The yellow filter, I forget this one all the time. Yellow is a combination of red and green, so red and green light would come through it. The blue does not pass, so what we would expect to see is that red light would pass through this combination of two filters. Here we have the magenta and the yellow filter. The magenta that looks purple because of this silly camera that is annoying me. And I'm going to put one on top of another. I'm going to put the yellow one on top of the magenta. And we get red. Huh. Isn't that cool? If I do it the other way around, I get that same shade of red. Oh, cool. It's nice when reality decides to follow your theory. Let's combine all three of those filters together. There's the red we saw before. And putting this one nicely here, I see that I can get a combination of green, I can get a combination with red, and one with blue. Awesome. Here we see all of those combinations. The first column is the different colors, the 8 different colors that we have. Here we see the combinations when we're mixing light on a computer monitor, for example. Red, green, and blue, all those combinations give us these colors. Now, if we're doing the same colors with filters, this is what we need. To get red, as we saw before, magenta plus yellow will give us red. Cyan plus yellow will give us green. Cyan magenta will give us blue. And finally, we get black by combining all three of them together. Let's try to summarize some of the conclusions here. Filters act differently than when we're mixing lights, monitors, tablets, and cell phones. Filters block light. That is, they make things darker. And sources, light sources, emit light. Light sources like flashlights and monitors and tablets, all of those, when they emit light, things get brighter. So they fundamentally act differently. Filters are subtracting light, and lights are adding light. Now let's get back to yellow, this confusing thing here. If we think about yellow in terms of mixing filters, which is similar to mixing paint, then we would expect that red and green are going to get rid of most of the light. That would explain why yellow is so contradictory to our natural thinking. The problem is that we're conflating the two things, an additive primary system where we're adding red, green, and blue, and a subtractive primary system where we're subtracting. Here we see some really pretty diagrams that illustrate both of those. On the right-hand side, we have the subtractive primaries, cyan, magenta, and yellow, and how they combine to give us red, green, and blue, and all three of them combine to give us black. Subtractive primaries, such as we use in printing. We'll talk about that more in the next class. And then we've got red, green, and blue, which are the additive primaries that you see on a computer monitor. Red and green combine to make yellow, red and blue combine to make magenta, and then we've got cyan, which is a combination of blue and green. All three of them on, we get full brightness on our display, and we get white. I'm not going to endorse any particular tattoo parlor in town here, but I do want to recommend that you get this tattoo. This is the Star of David mnemonic. A mnemonic is a way to help you remember stuff. With this diagram, the Star of David being two triangles here, we can show that we've got the CMY. Those are the, which primaries? The subtractive primaries. When we mix the cyan and the yellow, we get green. That helps us remember that. It helps us remember now when we're adding in light, when we're doing an additive mixture, red, green, and blue. The green and the blue together make cyan. It also allows us to think about, well, if we want to know what cyan light is made of, cyan is equal to green plus blue light. Finally, it gives us an idea. Oh my goodness, look at that typo. M and G. I'm sorry. I do apologize for that. M and G, magenta and green, are complementary. A magenta filter doesn't pass green, and a green filter doesn't pass magenta. Something else you might want to try on your own is take a look at something that's green. Take a look at something that's magenta. Look at a magenta spot on a screen. Stare at it for 10 or 20 seconds, and then look away to something that's white. And what you'll see is the complementary color. Summary now. RGB color theory encompasses all of this. We start off with a very simple idea. We can think of light as being a combination of red, green, and blue light. That's a simplification of reality, but it helps us to explain why we have RGB monitors, why we have RGB cameras, and why we print with CMY. RGB, red, green, and blue, those are called the additive primaries, and they're used when you're creating light with stage lighting, with computer monitors, etc., etc. CMY are the subtractive primaries that work with printing inks or paint or dyes. RGB color theory helps explain CMY, and the Star of David diagram helps us to remember how all of those combinations happen. I have a booklet that I put together. This is up on Canvas for you. RGB to LAB, color theory by the letters. I've gotten as far as covering this lecture and the next lecture. And by the way, the next lecture, we're going to apply the RGB color theory, the simplification of reality. We're going to apply that to print, and we're going to more closely understand how print works. So, I told you that RGB color theory is a lie, but a good lie. It's a good lie because it helps us to understand how computer monitors work and how printers work. But I should also say it's not really a lie. It's more of an approximation to reality, a simplification of reality that gives us a foundation to build on to understand color science.